Today, I want to introduce you to the complex power function, defined as w being a function of z, defined as a to the z, where a is a complex number that's non-zero. And the way a to the z is defined is e to the log of a times z. And we immediately see, because of the presence of this complex logarithm, that a to the z is going to be a multi-valued function. And in order to define it continuously, we need to define branch cuts. More concretely, we're going to have to specify the branch of the logarithm we're talking about. Otherwise, we run into trouble with results regarding complex exponentials. Let me give you an example to illustrate that. A nice example would be the multiplication of I to the I and I to the negative I. Now, how is I to the I defined? Well, that would be e to the log of the base I times I. And log I means that I have the logarithm of the absolute value of I plus I times the principal argument, which for the number I is pi by 2, plus 2 pi n times I, where n is some integer. So expanding this, I get e to the I times log absolute value I is log 1, which is 0. So I have I times I pi by 2. That would be I squared pi by 2, or negative pi by 2, that is, minus 2 pi n times I, correct? So that is what I to the I looks like. Similarly, I to the negative I would be e to the I negative I, that is, times log I, which we expanded as log absolute value I, 0, that is, plus I times pi by 2, plus 2 pi mi, where m is again some integer. So in this case, on expanding the exponent, we get this negative I squared, which is a positive 1. So we have pi by 2 minus 2 pi m times, we had I squared, so that's negative 1. So that's I to the negative I. We immediately see the problem of not specifying which branch of the logarithm we're talking about, because it's multi-valued. There are infinitely many outputs for a single input. So this implies that I to the I times I to the negative I does not, in fact, equal 1. It equals e to the, multiplying the two exponential terms, we have pi by 2 minus negative pi by 2, that is minus 2 pi ni, minus plus, that is pi by 2 minus 2 pi m. So these two cancel out, and we're left with e to the negative 2 pi. Why am I repeating the I unnecessarily? Terribly sorry about that. N plus m. And n plus m is just some other integer, so we have e to the negative 2 pi k. So we see that there is no guarantee that this thing here will be equal to 1. How do we fix this? Obviously, we just use branch cuts. That is, we specify which logarithm we're talking about. So if I want to define some kind of principal branch for a to the z, then I'll write this as e to the logarithm of a times z, where the argument of the base a, that is the input of the complex logarithm, is restricted. So I could restrict it between pi and negative pi. That's the default branch cut we use for the principal logarithm. And hence we define a principal complex power function in this way. And of course, we saw that any branch cut that restricts the argument to an interval of length 2 pi works for the logarithm. So an equally valid definition would be e to the z times log a, where the argument of a is restricted between 2 pi exclusive and 0 inclusive. Okay, that was pretty cool, but now let's make some observations of the complex power function. Now, to further study the complex exponential or the complex power function, I'm going to make a modification to the definition. Initially, I fixed the base and I varied the exponent. But now I'd like to define w as z to the a, where a is now a fixed complex number and I vary the base. And of course, it's understood that z cannot be 0 given the logarithmic way of defining the complex power function. So yeah, this is still a complex power function. We have a complex number raised to a complex number. And the first observation I would like to make is that if a is an integer, like let's say that a equals n, then w equals z to the n is nice and continuous. We saw that in, I think, the second or the third, yeah, it was probably the third or the fourth video in the series, that this complex monomial function is nice and continuous, just like and this case extends to complex polynomials. The problem arises when a is not an integer, and we can visualize this using complex planes. So our friends, the z plane and the w plane, are back. And let's study the behavior of a vector that starts over here on the positive real axis. So let me just mark this out as a length r. And this vector is r equals z, as in we have an argument of 0. So what I want to do is traverse this vector along a circular path in the counterclockwise direction. And when one full rotation is completed, I land back at r equals z. So we see that r has two polar representations. Z, that is, has two polar representations in this case. One is r, that is r times e to the I times 0, that is an argument of 0. Another polar form has an argument of 2 pi. So we have r times e to the 2 pi I equal to z. Okay, that was pretty obvious. I'm going to call this my starting point, and this here is going to be my end point. Now, let's check the behavior of this curve with special attention to the starting and ending points as we perform the transformation w equals z to the a and land in the w plane. First up, notice that for the starting point, we have w equal to r to the a. And this is a vector of length exactly that. It's a vector of length r to the a. Now, this motion over here in the z-plane can be picturized as a particle following the path a times e to the I omega t, where a is the radius of the circular path and omega is the angular velocity. Now, if you switch this up to a to the a times e to the I omega a times t, then you get a particle traversing a circular path of this radius with a new angular speed that might be slower if a is less than 1 and faster if a is greater than 1 compared to the speed of the original particle. So that means your ending point, the ending point in the z-plane, that was z equal to r times e to the 2 pi I, gets mapped onto w equals r to the a times e to the 2 pi I a. And this factor here is 1 only for the case of a being an integer. But remember, we're trying to study the case for a not being an integer. So that means you get a different vector. You get a different vector from this r to the a vector. And I can write this as a vector of length r to the a and of argument 2 pi I times a. And this diagram shows that a is less than 1. If a were, say, greater than 1, then by the time the particle in the z-plane completes one full rotation, the particle in the w-plane, the image particle, will complete more than one rotation. right? So you'll get something like this, something with an argument greater than 2 pi. The point is, we're picturing exactly how this function is multi-valued. And the only way to fix that is, of course, by introducing a branch cut. So we introduce our branch cut by using, again, the origin as a branch point. We can't let z be equal to 0. And let's make our branch cut along the positive real axis this time. So that means you start off with an argument of z being equal to 0, but you always have an argument of z ending up less than 2 pi. In that case, we fix the multi-valued problem, and now w is defined continuously. But wait, isn't that something we already know? Then what was the point of this whole visual exercise, right? Well, this factor was why I wanted to introduce these two complex planes. This is something called the phase factor. It's a factor by which the starting point and the ending points of the image in the image plane differ from each other. It's the factor by which the starting and ending points, the images of the starting and ending points, differ from each other, that is. Okay, now let's expand on this notion of a power factor. It's important because the power factor allows us to define some cool, and not only cool, but necessary branch cuts for functions that are not that nice in structure in comparison to the functions we studied before. For example, we've been studying the square root of z, but what if you study the square root of z times 1 minus z? What kind of branch cuts should we introduce in that case? Okay, so we're trying to build on complexity over here, studying complex analysis and trying to build up on already the levels of complex awesomeness. So let's start off simple. W equals z to the a, the cases outlined before, and we perform a transformation from the z realm to the z minus z naught realm, where z naught is some non-zero complex number. Okay, well in that case, w equals z minus z naught to the a. Now what does this look like in the complex plane? Well, if you took a guess and said that we can study it exactly the same way as before, only instead of having the origin as the center of our circular path, we could take the center to be z naught. And yes, you're right, that's exactly what we're going to do. So we start off with a complex number along the same horizontal line as z, that is having the same imaginary part. And we allow z to traverse a circular path centered at z naught in the counterclockwise direction. Okay, cool. So what exactly happens to this function here? Well, w equals z minus z naught to the a, and we could perform a transformation here by letting z minus z naught equal some other variable, call it zeta, whereby w equals zeta to the a. And this is exactly the same structure as z to the a, the case we studied initially. So you can visualize a zeta plane where we performed exactly the same exercise as before, and we see that the phase factor would be e to the 2 pi I a again. So what this means in the z-plane is that if you approach this point z from the upward direction in the upward sense, if you approach it in the upward sense, then you have f of z. And if you approach it in the from the downward sense, then you have f of z times e to the 2 pi I times a, which shows that this function has exactly the same power factor as z to the a. And because they have exactly the same power factors, exactly the same branch cuts will work for them to define them continuously. So in the case of this z-plane I have in front of you, if I needed the branch cut to be along this ray, that is z naught and all complex numbers to the right of it, then this branch cut will work perfectly well for z to the a as well. This will define it continuously as well. And vice versa, the branch cut that defined z to the a to be continuous will also work for this function as well. So any branch cut that works for z to the a also works for z minus z naught to the a, where z naught is some non-zero complex number. And that, I think, is a pretty cool result because it allows us to play around with branch cuts and visualize functions a lot better. Let me write one lemma and then give you some examples. So we have this lemma called the phase change lemma that states that if you have a structure f of z that equals z minus z naught to the a times g of z, where g of z is a single valued function, then the phase factor of f of z is exactly the same as the phase factor of z to the a. That is, it is e to the 2 pi I times a. Now let's look at a few examples. So I'm going to take a few examples from Gamelin's text over here. The first one is f of z defined as the square root of z minus z naught. Here the phase factor equals e to the 2 pi I times a, which in this case is 1/2, and we have e to the I pi, which is -1. So as you complete one rotation in the z-plane, you see an inversion of the sign in the image plane. Okay, cool. Now let's look at a few more examples. Let me start with the function f of z defined as square root z times 1 minus z. How exactly can we define this function to be single-valued and continuous? Well, if we write this as a product of functions root z and root 1 minus z, and we talk about a branch cut for this function here, we know that any branch cut that makes square root z continuous will also work for the function square root 1 minus z because it's the same phase factor, right? So that means we could define f of z to be continuous on a slit plane, c excluding -infinity to 0. Equivalently, any branch cut that makes this function continuous also works for the function square root z. They have the same phase factor. So we could define f of z to be continuous on the slit plane c excluding 1 to infinity as well. And there's a third slit plane to define f of z continuously too. And for that, again, we're going to need some visuals to explain things. So I have two z-planes, each one dedicated to the study of square root 1 minus z and square root z and square root 1 minus z, as z traverses a unit circle centered at the relevant branch point. For the first case, I have this branch point at the origin, z equal to 0, and along this unit circle, if I approach z equal to 1 from above, I get 1, right? But if I approach it from below, I get -1 because of the phase factor of e to the I pi. Okay, cool. And for the case of square root 1 minus z, I have this branch point at z equal to 1, and if I approach z equals 2 from the upward sense and from the upward direction, then I get square root 1 minus 2, which is I. And as I approach it from below, because of the phase factor of -1, I'll get -I. Now, how can I combine this into a single z-plane diagram with a branch cut that defines the function to be continuous without the branch cut having to be of infinite length? To achieve our ambitious goal, I've drawn out another complex plane, this one highlighting both branch points 0 and 1. And if we consider a complex number z sub 1 lying on this strip of the positive real axis connecting 0 and 1, then if we approach it from above, we get f of z sub 1, whereas from below, we get -f of z sub 1, which is a bummer, so there's a discontinuity. But what if we approach a complex number z sub 2 outside this strip? Well, if you approach it from above, then you get f of z sub 2. Whereas if you approach it from below, then you get f of z sub 2 times a phase factor of -1 because of square root z, and a phase factor of -1 again because of square root 1 minus z. So this is f of z sub 2, which means that our function is continuous outside of this strip. So the branch cut we need is this line of unit length over here. So we can define f of z to be continuous on the slit plane C excluding 0 and 1, which is pretty cool. And there's a nice exercise in Gamelin's text that sort of generalizes what we've seen so far. That is, if you have a function f of z defined as z to the a times 1 minus z to the b, then what are the values of a and b that make f of z continuous on the slit plane C excluding 0 and 1? We see that the branch points are, yes, in fact, the branch points are 0 and 1. So carrying forward with our previous logic that outside the interval 0 to 1, we need the phase factors to be canceling out, as in the phase factors e to the 2 pi I a because of z to the a and e to the 2 pi I b because of z to the b. They both need to be equal to 1 on multiplication, which implies that e to the 2 pi I, oh wait, terribly sorry about that, 2 pi I times a plus b should be equal to 1. But this only happens when a plus b is an integer. So that's the solution to the problem. And I'm just going to take a look at two more examples to make things even more clear. Another example would be the function, again, this is from Gamelin's text, f of z equals square root 1 minus, no, it was square root z minus 1 by z. And of course, we can write this as square root z squared minus 1 by z, or root z minus 1 times root z plus 1 divided by root z. What branch cuts would make this function nice and continuous? Now, there are 3 branch points to consider here. So we could define a branch cut to be along this line, along this interval from 0 to 1, and that would work. But if you traverse a circle of big enough radius, then we see that again we're going to be crossing the negative real axis, and we have this branch point at -1 that introduces a phase factor of -1 once again because of this function. So we're going to have to make our branch cut more sophisticated by excluding this part of the negative real axis. So in order to define f of z to be continuous, we need to define it on the slit plane C excluding the interval -∞ to -1, as well as the closed interval 0 to 1. That's how you can define this to be continuous. One more example would be the function f of z equal to square root 1 minus z squared, which can of course be written as 1 minus z times 1 plus z, all in square roots, of course. And in this case, we see that we have 2 branch points at -1 and +1. And this is quite similar to the case of, it's exactly the same case, that is, of square root z times square root 1 minus z. So the suitable branch cut would be this interval here. So we define this function to be continuous on the slit plane C excluding -1 to +1. And I think that's enough examples for this video. I hope you enjoyed the video. I hope you learned something. If you want to look at some practice questions, then I'm not going to assign any homework today. You can look at exercise 1.8. I think that's the exercise at the end of the complex power section in Gamelin's text. You can look at that textbook. You can look at that exercise for problems. In case you need any help, you can DM me on Instagram. All links are in the description box. I hope you enjoyed the video. Once again, I hope you learned something. Thank you. See you next time.